So in this talk, I will be giving you introduction and then advances in Raman spectroscopy, starting with the normal Raman or called dispersive Raman, then you have micro Raman, then nano Raman, and then there are more recent varieties which are applied, and then some applications from the nanoscience area. So Raman spectroscopy is about actually light matter interaction, even without physics background. This is, I think, high school stuff. And when light falls on some material, you have so many kinds of phenomena. Some part is reflected, some part is transmitted, and some part is scattered. So, and then scattering can be of elastic, where there is no change in energy, and it can be inelastic, where there is change in energy. So, whatever you see in everyday life is mostly actually elastic scattering of light. And what we will be talking about today is actually one of the inelastic scattering phenomena, which was discovered by Raman way back in 1928. So this behind every discovery there is interesting story. You should be reading all this, but actually all this started with the question when he traveled to the Mediterranean Sea in London while traveling, and deep blue color of the sea actually made him think what could be the reason, because just a glass of water, inside the glass water doesn't look any color, but the same water inside the sea, on the sea, appears blue. So his boss, immediate boss, Raleigh, was actually with him while traveling, and he actually explained that it is due to the scattering from the sky. Sky is blue, so the same blue light is scattered by the sea, we see blue. But Raman did not believe in it, and then he went on to discover this phenomena that it is something more fundamental. He was actually studying all these optical phenomena and sound, particularly musical instruments, for many years. And he was right from the beginning a prolific scientist, and you can see his biography. But so as I said, all this started when he went in a voyage to Mediterranean Sea, and his selection also in this Oxford meeting was also that is also one story. But basically, this discovery of Raman effect is actually put the quantum theory in very solid foundation. So he got support from many big physicists like Niels Bohr and Robert Wood, and he got eventually Nobel Prize and Bharat Ratna Award. So today we will be discussing about importance of this technique. It started with just some basic physical phenomena, but we will see its application in so many areas, starting from material science, then pharmaceuticals, polymers, bioscience, nanotechnology, and we have these Raman machines, commercial machines, like this is Raman spectrometer coupled with microscope. This company machine we are using more advanced version, and then there is another company which is called Renishaw. They also make Raman spectrometer, and you have more advanced version of Raman like confocal. This is more expensive. Then latest one is actually this deep enhanced Raman spectroscopy, which is there with us in the Center for Nanotechnology, and it became so popular that you can have like multimeter, handheld multimeter. You have also handheld Raman spectrometer, which is used for identification of explosives and chemical weapons, etc. You can take it to different locations and do field study, and eventually this is also applied in some fancy applications, like you can identify real pearls from the artificial pearls. You just carry your spectrometer in a hand, go to the market, and you want to check whether they are selling real pearl or not. You could real pearl should have only one this Raman peak, whereas artificial pearl will have many peaks. So that way you can identify, and people also take it to the space to know Mars surface. You can see what are the composition there, different from how it is different from the Earth, and then whether people can start living there. So living conditions, people try to explore. So scientific exploration has no limit, and that is how from the fundamental discovery going to so many kinds of fancy things, applications. So this is the facility you have in the Center for Nanotechnology. This is one of the bread and butter for us, and this is actually working all the time, uninterruptedly, compared to many other facilities. Maintenance is an issue, but this is the instrument which is actually serving a lot of students in this IIT, and you will have opportunity to visit this. So this is where you have the spectrometer with microscope, and this part is actually AFM coupled with it, and that's why it is called TARS. I will talk later a little more about it. So basically this Raman spectroscopy is inelastic scattering of light which is caused by quasi-excitations, like we have the elementary particle, electron, proton, neutron. Similarly, you can have something called phonon, okay, and then you can have, so basically Raman in general for a molecule, it actually looks into the vibrational modes. When you shine light, your electrons get excited. Apart from that, your atom as a whole also can vibrate because of the additional energy. So because of that, you can have vibrational modes, and you can look into the phonons in the crystals, or magnon, plasmon, so many other quasi-particles in physics we have. So you don't need to really worry about many things, but just about these vibrational modes of the atoms and molecules we are bothered in this Raman scattering phenomena. Okay. And interestingly, this inelastic scattering was actually predicted about 5 years back, before Raman went to discover this phenomena. Of course, he did not read this theory before discovering that the blue sky is due to this. And he had the backup of the theory. That's how this became so very important discovery. And even though it was predicted theoretically, it was very difficult to detect such small light, because whatever light intensity you put, like you put this laser is typically milliwatt, okay, some 2 milliwatt, and the Raman scattered intensity will be nanowatt. So it's extremely difficult to detect. But it was the genius of Raman who actually discovered ways to detect extremely small amount of light. And of course, the studying was not with nanowatt light; it was with big amount of liquid sample, and he could do it. So basically, in recent days, that is 70 onwards, discovery of laser, with the availability of laser, Raman became much more practical. Otherwise, setting up Raman spectroscopy is very, very difficult. It's one of the toughest technique to set up. If you have the spectrometer, easy to get the spectra, but making one, particularly physicists try to do that, assemble things and get lasers. So, and then you have so many varieties of laser, like near infrared laser, which are particularly applicable for the study of biomolecules. And we have continuous wave laser and pulse laser. So you have many varieties of Raman which have come up with time. Okay. So without going much details, I'll just tell about some basics in 2 slides. That when you shine light like laser, I'm shining on the screen. Most of you are seeing the laser because most of the light is actually reflected or scattered without change of intensity. But there is some light which you cannot see with your eye, which is changing the frequency or the color, which you cannot see. So most of the light which reflects is same wavelength or frequency which is called elastic scattering, and that intensity is like 99.59%. Not even 0.00001% is the inelastically scattered light. So this one, which is elastically scattered, is called Rayleigh scattering, and that's why we see why the sky is blue, because the scattering of the ray, the blue color has the high scattering cross section from the atmospheric particle, so we see blue sky. But this Raman scattering is actually inelastic scattering of photons which are excited to a higher vibrational or rotational energy levels. Okay, so as I said, when you shine light, there is photon. How this Raman scattering discovery led to the foundation of quantum mechanics, because quantum mechanics actually proposed about quanta of light, and that was actually explained first by Einstein in the photoelectric effect. And then this quantum of energy, h nu, has to fall here, so there the frequency comes, and then Raman selection rule comes also in the quantum mechanics. I will not go into all those details, but in Raman scattering, only 1 in 10 billion photons actually does this elastic scattering. So what you see is not even 1 in 1 billion, 1 in 10 billion only is getting Raman scattered. That's why scattering cross section is extremely low. It's very difficult to detect. And Raman spectra means you are looking at the change in the wavelength, or in terms of the wave number given by this. There is a reason why we express in terms of 1 by lambda instead of just frequency or lambda. Okay, so Raman spectra is plotted in terms of the shift in frequency with respect to incident wavelength and the intensity of the scattered light. So this is showing the basic diagram. This is called Jablonski diagram. Many chemistry, biology students will be familiar with it, where you have these basically. So particularly in case of Raman, we are actually looking into this virtual energy states. Okay. So in case of atoms or electron getting excited, you have excited state of electronic states. But here we are talking about vibrational states or virtual energy states of these electrons, from where if you have decrease in energy like this one, it is excited and scattered light is having lower energy, then it is called Stokes scattering. And if the scattered light is having higher energy, which is usually again very low probability than the lower energy one, so this one is called anti-Stokes Raman and this is called Stokes Raman. Okay, so most of the light actually goes through this Rayleigh scattering, but you have some light which goes to Stokes scattering and anti-Stokes scattering. Depending on the spectrometer, most of the spectrometer is equipped with the detection of Stokes scattering, not, and these are the time scales of the scattering events. So Raman, of course, based on some selection rule, these are typically taught in spectroscopy course, and there is basically why these things happens. There is basically polarization change. Okay, because light means electromagnetic field, and that induces some change in the atomic configuration. So there is a change in the polarization, and that gives rise to this Raman scattering. Apart from so there is this is a classical theory of Raman scattering. Very simple mathematics. Basically, like you have a time variation of the dipole moment, which is caused by the incident radiation, electromagnetic field. So basically, this is your polarizability, and we know the dipole moment is alpha into E. E is the electric field, and if these are time dependent, you have this. And so in general, they will the electrons or atoms will oscillate with the frequency of the incident light. But if it is different, the internal frequency is different from the incident frequency, then you will have basically if the incident radiation has frequency omega and probability of the molecule changes between this alpha minimum and alpha max, then at a frequency of omega internal, means this is your incident frequency and this is the atom's own frequency, fundamental frequency, then you can write this alpha in terms of alpha naught plus this delta time dependent and this one cos A cos B. If I expand, I will actually get 3 terms. So this is how you have one term which is having with the incident frequency, and that is actually the Rayleigh scattering, and then you have another with omega minus omega naught, means lower energy transition, and there is omega plus omega naught, higher energy transition. So these are 3 lines which you see in the scattering, which is shown through this energy diagram. So this is a typical Raman spectrum of most common chemical carbon tetrachloride. Whenever we try to set up some Raman machine, we try to test it with this. But you see, this is the incident light, which is very strong compared to the Raman scattered. These are anti-Stokes, these are Stokes. So Raman shift is positive, that is giving rise to Stokes lines, and each of these corresponds to some bond in this carbon fluorine containing compound. So each of these actually are characteristics of certain bonds which are to be confirmed from other studies. You have to have some library of data correspond to each of the compound and each of these bonds. So what information can you get from this spectroscopy in material science and nanoscience? So just the characteristic Raman modes. I should have some idea of what is the composition of the material, and then from the known modes, if it matches with these observed spectra, then you can talk about composition of the material, like whether it is like MOS2 or it can be MOS3 or whatever. This is one of the molecule, the solid we study. This is basically layered material. We have a lot of activity on this. That's why I took this example. And if you have, suppose you are studying a known material, you know, suppose most standard material in solid state is silicon substrate, good for electronics. So silicon has got a peak at say 520 centimeter inverse in Raman. But if you study silicon, your own make sample through some deposition technique, and you see a peak shifted different, then change in frequency corresponds to strain or stress in the crystal. So if it is compressive strain, then the peak will shift towards the right, higher wave number. If it is tensile strain, it will go to the opposite side. Similarly, it can talk about the crystal symmetry and orientation from the polarization dependent Raman. Like if the incident light, you send polarized light and then look at the scattered light, you can actually talk about polarization or symmetry of the molecule. This is particularly true for like say chain type of molecule, where it is you can see asymmetry, one dimensional one. So even in case of diamond, CVD gold diamond, you can have great orientation from these kind of studies. And width of the Raman peak tells about the quality of the crystal. So you can have also stress strain will actually do the not only shift, it will do broadening depending on the whether it is homogeneous strain or inhomogeneous strain. So if you have inhomogeneous strain, you will have broadening also, and that corresponds to plastic deformation or local strain. Homogeneous strain means local strain. And then intensity of the peak tells about the amount of the material or the thickness of the material. If I get very low intensity peak, that means my sample volume, particularly you can have some substrate and some thin film, and if part of it is not crystalline, then you won't get high intensity peak. So that way you can talk about volume of the crystalline edge or the thickness of the layer. So these are the basic guiding principle for studying the Raman spectra. Then you have more things with the advancement in the Raman technique. So this is the basic Raman spectrometer where you have a light source and then it goes through some mirror, polarizer, etc. To the sample through some prisms or notch filter. So overall the instrumentation is a bit expensive, it's not so simple as I said, but once you have the spectrometer, life is simple. So the machine will have cost about 2 crores. And you can make your own Raman spectrometer in 2 lakhs also, but it won't be as good as 2 crore. So there is sophistication, there is automation, and what I am talking about is like an assembled setup. Okay, not the spectrometer which you see in the center. So you have basic light source, then you have spectrometer, you have the sample here, and then you have the detector. So there are a variety of light sources, like you can have this Mercury lab. When Raman did the experiment, that time laser was not there, so he was using just the Mercury lab and the sodium lab, which are used in your teaching lab, you know. Okay, so later all these lasers came, particularly the argon laser and then helium neon laser. This is the most common line of the helium neon laser. You also have NDR laser giving infrared light, and argon ion laser giving you 488 nanometer, 532 nanometer, etc. They are the most common one. So as I said, 1 in 10 million means 1 out of 10 to the power 7 photons you are actually trying to detect. So why all this Knox filter? That actually rejects the direct light. Your scattered light will contain also the original light, and that you have to reject. So for that there is something called Knox filter, which is again very expensive. So most common one, as I said, is 488 and 514 taken from the argon ion laser. They are good for semiconductor, catalyst, biological, polymer, mineral and general purpose. But for specific purpose, you can have, like for wide bandgap semiconductor, we can use this UV laser, 325 nanometer UV laser. This is much more expensive than this. And for this is good for resonance Raman, that I will discuss what is that, resonance Raman. Also 244 nanometer laser, and then we will also use 633 785, particularly for the sample which gives fluorescence. We do not want fluorescence in the Raman because fluorescence intensity is much higher than the Raman. So Raman you cannot detect if there is a fluorescence happening. So that's why these IR lasers are used in many cases, and depending on the wavelength, suppose you are using low wavelength, but wavelength scattering cross section is inversely proportional to wavelength according to physics theory. So I should have better scattering, more signal from lower wavelength excitation, but it it monitors much lower volume, so it cannot go to much depth. So higher wavelength, higher is the relative volume of the sample. Okay, and then spectral resolution is very important. So in Raman spectroscopy, you are talking about change in the frequency of the light by very small amount. It's not in electron volt, it is not even in milli-electron volt, it is even much smaller than that. So in terms of wavelength, if you have just 1 nanometer shift in wavelength, that is also great in Raman spectroscopy. So we need very high resolution spectrometer for Raman, designing a Raman spectrometer. That is why it is quite costly. And see here, 1 nanometer is equivalent to, in terms of this Raman, as I said, is plotted in terms of inverse of wavelength. And this 1 by incident wavelength and 1 by scattered wavelength this difference is expressed in terms of centimeter inverse. You have to do this conversion from inverse nanometer to this 10 to the 7 factor. So 1 nanometer actually corresponds to about 40 centimeter inverse in Raman signal. Okay, so depending on the wavelength, you will have different. Suppose I am using the UV excitation, which has got better scattering cross section, better depth, but the resolution I actually lose in terms of. So I need to have very high resolution spectrometer. And the modern Raman spectrometer that actually uses CCD instead of just the normal detector, and we can have remote Raman also these days, which are fiber coupled light source and probe head, means we don't need to take the spectrometer to the field. We can connect with fiber and then get the signal with the help of this fiber for the light source as well as probe head. And then we have Fourier transform Raman spectrometer, which uses Michelson interferometer, particularly for the fluorescent material or biological samples. And then what machine we have is actually micro Raman spectrometer, where you have a microscope attached to it, and then with using this you can do normal spectroscopy as well as mapping of the chemical composition of the sample. And then to get higher resolution, there is something called confocal microscopy, which is also applied in Raman microscope. So these are more recent advances. And then you have deep enhanced Raman spectroscopy, which I will be just briefly touching upon. And these are the typical detectors. Most common is the photomultiplier tube, earlier days, but these days people use silicon CCD, because with CCD you can get the whole spectra in a moment, within a second. Whereas if you use this photomultiplier tube, which has got higher sensitivity of detection, but it takes time to collect the light, because there is an integration time involved. And if I am working with IR laser, I have to have this gallium arsenide detector, which are good for IR thing. So this is showing one simple micro Raman spectrometer. So whatever spectrometer I showed, source, monochromator, detector, etc., will be there inside this box, but the light is actually falling into the sample through a spectrum, through a microscope, and also the scattered light is collected through the microscope. So that is the microscope integrated with Raman spectrometer is called micro Raman. Okay, it has got several advantages, like you have confocal light collection, high lateral resolution, and excellent depth resolution, large solid angle of collections of light. Because using normal the lens, you can actually make a spot size of millimeter, whereas using the microscope objective, you can go down to micrometer. And this confocal allows you to go to even 100 nanometers. So that way spatial resolution is very much enhanced, and then you can do at different spots and go along the line. So that way you can do basically over some area, so that is called imaging, Raman imaging. That means you do collect spectra at different points at equal interval, you move your laser or sample step by step, and then you get sort of continuous this thing. So this way you can have line mapping and eventually over the whole area. So this way you can generate a map of your whole area to know the uniformity of your. Suppose you have to make a device, you need certain area. Is it uniform? That very much matters. So in case of confocal Raman microscopy, apart from all light source detector, you have some pinhole in between. The incident as well as the detector side, there is a pinhole which actually rejects the out of focus light and collects only very small spot at a time. So that way, not only you improve the spacing resolution.
3D spectroscopy means you can do depth profiling of this. This is a more advanced version. I will not go into details. So this is one of the. We have confocal microscope, but that is working in the fluorescence mode, not in the Raman mode. So you can actually detect stress in silicon like this one. You see different kind of contrast around this. This is a silicon wafer and there is some damage here. So around the damage you can see contrast, so that says stress profile in the substrate. If you have some dust particle, you can also look into these with this kind of contrast. So this is Raman mapping, not ordinary microscope which works with the reflection or transmission mode. Wood cell, you can see there are different layers. Similarly, living cells imaging, these are all Raman mapping. You can look into the tablet coating or textile fiber, and so many examples of Raman everywhere people use. This is one like drug coated sphere, like you have some coating over it. Like sometimes the medicine is very bitter, so they coat with some nice tasty things, and you can see whether it is good for your health or not using this kind of mapping. So you see here the compositional profile from Raman. So what you get from ordinary spectrometer is this, but if you do mapping, you get this kind of compositional image from the Raman. Okay, now I go to the advanced Raman spectroscopy technique. So one of them is called resonance Raman spectroscopy. So here in this you excite, when excitation wavelength should be chosen such that it matches with the electronic transitions level. Like I have a material with certain band gap, and if I excite light which is mapping matching with this band gap of the material, then I can have electronic transition apart from the vibrational level, the quasi-states transitions. So in that case, your Raman signal is heavily enhanced. So this is called resonance Raman. So for that you need, of course, variable wavelength light source, which is a bit expensive. But we have some 4 or 5 wavelengths you can choose for your material. We do this for our research. And another technique which is very versatile, everybody uses, biologists, chemists, physicists, is called surface enhanced Raman scattering, which was discovered way back in 1977, but still a lot of research is going on in this. So here, like here you have about 10 to the power 2 enhancement, but here you can have enhancement of the order of 10 to the power 8, means 100 million times enhancement of the Raman signal. So this is remarkable. With this you can actually detect even single molecule today using this surface enhanced or tip enhanced Raman spectroscopy. So basic idea here is that you have some metal nanostructure below the sample. Whatever substrate you have, over that you put some metal nanostructures, over that you put your sample, your signal will be enhanced many folds. It could be up to 10 to the power 8, but typically you get 10 to the power 6 kind of enhancement with metallic nanostructures. The nanostructure size could be 10 to 100 nanometer, particularly using the gold and silver nanoparticle. And I will show some examples from our group where we have used non-metal nanostructures to get this source later. Okay, and then there is a technique called tip enhanced Raman spectroscopy, which is the facility we have, but it is one of the most difficult technique to set up, where you have to combine AFM tip to focus light into the sample from the micro Raman spectrometer. And the goal is that you can get spatial resolution down to 20 nanometer. Because normal light you cannot focus below micrometer because of the diffraction of the light. It spreads. But if you use confocal, you can go to 100 nanometer. Whereas here, if you use this tip enhanced Raman, because of the metallic tip of the FM, you can actually focus the light to 20 nanometer size and detect features, particularly molecular